Mostly it's graphics, and I do sometimes dabble in the dev relations and best practices and other stuff as well. And so if you have any questions relating to the PC Rift, specifically for the DK2 and the upcoming stuff, I'm pretty much your man. Other than that, I had a brief stint where I was developing my own game, and actually I still am. It's just, let's consider it kind of shelved for now. The game is called Black Space, and it's being developed specifically for the PC. And it's actually currently greenlit on Steam. If we get a chance, even though it's completely separate from what I do at Oculus, I do want to briefly share because it does relate a little bit to what I'm going to talk about today as well. And then prior to all this, I spent about a decade or so working at Electronic Arts, specifically in Tiburon, which is the office in Orlando, Florida. And over there, I spent about 3 console generations, about, I want to say, maybe 10 plus titles. My main focus and expertise is actually on photorealistic rendering in real time, but then I've also had the chance to work on a bunch of other stuff along the way. So, a brief overview of what I actually want to talk about today. We're going to briefly go into the hardware side of what we utilize in VR, and maybe get a more specific glimpse of the things we do for Oculus, and then go a little bit, maybe geek out on the software aspect of what it takes to render a VR application. And then I'll go into how VR software differentiates itself from some of the other real-time applications some of you guys might have dealt day in, day out. And then the up-and-coming trends of what we're seeing around as far as games and other applications go for VR specifically. So we always see these photos of people trying on VR headsets. They're amazed. Their mouth is open. It's kind of like the VR face, as you might call it. But then, even though we know VR is awesome, it's also really tricky. And it's kind of because some people think VR is really just about, oh, you know, you just render 2 eyes and separate, and you're almost kind of good to go. It's really all just about graphics. When that's really just tip of the iceberg. Of course, graphics is a whole thing that you need to talk about, but that's just one tiny aspect, so to speak, of what it takes to get good VR going. And then specifically for a headset like the one you see on the side, that's the up-and-coming Oculus Rift CV1 that we've announced. That's going to come out in 2016, early 2016 in fact. And when you look at that headset, you realize there's a lot of very special components that you don't get to play with on a regular game, or you don't even have to be aware of it, like the optics, the fact that you need really good quality of service, where that means you need a very precise and accurate stream of data, and you cannot drop anything. You have to process all the data coming through. Otherwise, the experience really goes bad really quickly. And then you have to worry about accurate timing and all these things. And, of course, maybe one of the most important things with VR is that because this is a headset that you wear on your head, you have to be aware that you're dealing with different people, and different people react differently, and you need to make sure you're catering to their physiology. So, when you look at the hardware, especially this open view of the CV1 that's going to come out real soon, you quickly realize it's got some really specialized screens. In this case, there are 2 separate panels, each with a resolution of 1080 1200, giving you a total of 2160 by 1200. And then we have very special lenses that are catered towards giving you the best fidelity that is currently possible. And then, as you all know, there's the IMU that you also kind of have in your phones, but these are really high quality. They operate at 1000 hertz. And give a constant, very accurate stream of rotational and acceleration info. On this headset, we also have the microphone and the camera for pretty much obvious reasons. And you also see those gray LEDs like there and there and there. And those are the LEDs that we use for tracking the position of the headset when you're moving around. And that in turn works with the IMU. So when you get your headset early next year, this is going to be what's coming out of the box. The one on the far left is the positional tracking camera. That's going to be tracking the LEDs that are actually hidden behind the panel and also behind the fabric on the top and the sides. And we also have a controller that's coming with it, because we know that even though motion-tracked controllers are cool, a lot of developers currently don't have the expertise to make full use of it. And by the time that is going to happen, we already have our position tracking controllers coming out. And at that time, it'll be a full-blown experience. In this picture, you see the half-moon prototypes with the exposed LEDs on the side, which is pretty much what our previous Crescent Bay demos also look like. And expect a much more refined version to come out early next year as well. So when we look at the software aspect of VR, you notice that it's, again, not just rendering. There's the fact that you're dealing with tracking. You need to make sure that you're very accurately predicting the position the headset will show up somewhere into the future. And this actually very much applies to the controllers as well. We internally do a lot of work in the SDK side, so the only thing at this point the application needs to worry about is just making sure they're rendering the stereo eye pairs, and then they hand them off to the SDK. And the SDK ends up doing what we call time warp and then distortion, which is what allows the headset to show really high fidelity VR. So right off the bat, I do want to point out that everyone here can just go onto our website, create a user for themselves, and go and download our SDK and actually peek into the code, see all the stuff that we're doing, start crunching on some really cool experiences. And it's not just the PC SDK, obviously, even though that's the area I'm currently focused on. We have our audio SDK, we have all the plugins that go into Unity and Unreal and all those things. So not only could you develop, but you could also find out a good deal of stuff about VR by looking at the code in there. So when you look at the software of what a VR application does, now this is the part where I'm going to go a tiny bit into detail. Some might not be aware of all the intricacies of why VR is interesting from a software point of view. So the camera or the IR sensor that I had shown operates at roughly about 60 hertz, and it is the thing that recognizes all the LEDs that are hidden behind the front panel. And then as you're moving around, it tracks the dots, and then that in turn is combined with the 1000 hertz IMU, which gives you the gyro and accelerometer info. Together, what we call sensor fusion is applied, where both that 60 hertz data and the 1000 hertz data is combined. And ultimately, on the user end, what that means is you just get a 3D position in space, and that happens to be the position of the headset. And then from there, you can deduce the positions of both the eyes. So what happens there is it gives you a continuous series of information over time. When an application wants to start rendering, it has to say, well, give me the position of the headset. The problem is you don't actually want the position it's currently at, because by the time you render the scene, it's going to be historical data. What you want is forward predicted information. So when an application is starting to render, usually you want some kind of latency of maybe 20 milliseconds, which is actually deduced on the fly, and the SDK actually provides this out of the box for you. So you say, give me the position and the rotation where it's going to end up 20 milliseconds into the future. And then the application renders both the eyes. Let's say that takes about 5 to 10 milliseconds to render. And then this is the part where we go into the time warp aspect. After the application gives us the two eyes, we, as the SDK, take those and we recalculate what the position and the rotation of the headset is going to be, because the closer you get to the point that the image is going to be shown on the screen, the lower the prediction accuracy, or sorry, the higher the prediction accuracy, but the lower the time to predict into the future. So we get a more accurate reading, we apply our time warp, and then the SDK does a series of steps of refining the information where when you look on the PC screen, you'll sometimes see that, for example, the colors look split. In fact, even though on the PC screen it might look strange, actually on the headset, we're correcting what would have looked ugly in the first place. So after that point, the interesting part here is, and also probably very different from some of the other virtual reality SDKs you've seen, is this notion of time warp that I've just talked about. The idea being that when you reproject the scene, you're getting better fidelity. And in itself, it has three separate stages, or three separate things that we actually account for. One of them is the fact that because we're doing a late reread of the orientation and position, we get better, more accurate info. And then we also do this interesting compensation, because when you look at an HMD screen, we do what's called a rolling shutter. On the DK2, for example, we light up the screen from right to left, because you can think of it as the cell phone screen turned sideways. So it goes from right to left. And in the time warp calculations, we actually account for this, and we correct that so you don't see any awkward, strange rotations in the image. And then on top of that, when the application might not be able to hit frame rate, normally with the CV1, we're asking that the application renders at 90 frames per second. That's pretty ridiculously high. But people have to get used to this notion, because it's actually really a requirement. So the deal here is, though, we do want to smooth the process. We realize that a PC is not always going to be something that never gets interjected by other info happening on the PC. So every now and then, if the application happens to drop a frame, our SDK is, we are actually actively researching the ability to do what's called asynchronous time warp, where if the application drops a frame, we kind of fill in the data with what we think should have been shown on the screen. That way, the image ends up being much smoother than you would have expected. And actually, to that point, if you look at the blog post where I'm giving the link, you can definitely read up more on that. So yeah, I mean, all of this sounds really simple, but when you look at VR, timing is ridiculously important. If you don't get your predictions right, you're going to induce some strange situations that you wouldn't have wanted otherwise. And the problem here is that if you have incorrect prediction, it's very tough to see. Even at Oculus, very specific people happen to be able to notice prediction values that are off by 10 milliseconds or so. So when you look at that, it ends up being an interesting thing to try to push towards. And then because we're dealing with PC, we need to also account for the fact that the hardware can be very different. Some people have multiple GPUs. Some people accidentally enable power management. Some people have strange USB hubs that end up just starting to buffer up data when in fact it should be streamed as far as possible to the host. So all of these end up being strange things we need to worry about. And then, like I was saying previously, there's the human variation factor, where each user is different, they have different tolerances, and we try to make sure that we're within the tolerance of pretty much everyone. That's actually one of the reasons, for example, why we're pushing to 90 hertz and not claiming that 75 hertz on the DK2 is good enough. And then people who have coded games or other real-time applications might think that they know everything there is to know about making a VR application. And the problem there is that some of those intuitions are actually wrong. And a lot of people have said this, and I'll reiterate that you need to keep on experimenting when you're doing VR applications. Don't expect that what you try the first time is just going to be okay. And again, when we look at timing, I've been talking about how we do a lot of predictions into the future, and you need to be absolutely accurate and also have really good quality of service, where for some reason, if your USB is accidentally buffering data and things come out a frame later, you have to have a way to account for that. Luckily, in our SDK, we do account for that because every information coming out of the headset is coming out with a real-time timestamp, which is synced against the timestamp of the CPU. So even if something is coming out a frame late, obviously it would be better if it doesn't come out a frame late because that will ultimately alter the prediction that's happening. But in this case, we do account for certain unforeseen issues. And then, like I was saying, it's really tough to see incorrect timing. The problem here is that even though you might think your application is working fine, you're like, oh, you know, I just ran it for 5 minutes, I'm testing, yeah, it looks good, I'll just check it in and call it a day. The problem is, 15 minutes later, people will start to feel nauseous. And you won't realize that because you're maybe constantly running the application, putting on the headset, trying something, running it, and you never actually immerse yourself into it for extended periods of time. Your users are going to be the ones doing that, so you need to actually take the time to do that as well. You could call this presence VR, but the problem here is that the more you make an experience make you feel like you are in some other place, the more you have the chance of making people freak out because you'll get them nauseous or they will start reacting negatively to any little thing that doesn't quite work the way you expect it to. And some bugs and design issues can easily pull you into this problem. So some of those things that you need to look out for example, the world scale. In VR, you need to make sure the world scale is accurate for every single person individually. That includes the interpupillary distance to make sure that the distance between your two eyes that is defined in real life is also taking place in the VR application. Or you need to make sure that not only the interpupillary distance, but now that we have position tracking in the DK2, your head motion side to side is also being accurately scaled with the interpupillary distance. If you want to change your interpupillary distance to be half the distance, you want to make sure that your head motion scale is also half the scale. Otherwise, people are going to, again, get nauseous real fast. There's also the other kind of sort of unknown where you need to, if you're embodying, if you're creating a VR application, which is a first-person experience, and the idea is that you're trying to make them feel like they're in a human body in that world, you do kind of need to make sure that the height is accurately portrayed in the VR application. But that can get somewhat fuzzy because it depends on the kind of experience. You know, if you're walking through the world, if you're sitting, if you're lying down, which gets really tricky. But the physical dimensions, and also there's the notion of the floor dragging effect, where if you're in VR, if you're sitting, but in real life you're standing, or vice versa, and the vice versa is more consistent because people tend to sit in front of their computer, whereas the first-person experience, you tend to walk around in that. All of a sudden, the world scale looks weird, and you just stand up and you're like, oh, it was actually correct all along. It's just the fact that when it starts to depend on where your feet are positioned, strangely enough. And we found funny ways to work around this, like you can sit on a bar stool where your body knows that you're actually elevated above the ground, but even though you're sitting, then your brain thinks that it's kind of matching one-to-one with what you see in VR. And those kinds of things are things that you start to worry about. So one of the other problems is this notion of vergence and accommodation conflict. What vergence means is how much your eyes converge or diverge based on how far the content is, and accommodation is how much the lenses in your eyes dilate to bring something into focus. Now the weird part is, this has been around all along. It's not something new to VR. When you go to a 3D movie theater or you're watching something on your TV that's on a 3D HD TV, this has been there all along. The interesting thing is that directors are usually aware of this problem, so they tend to avoid bringing things right up against your nose. In VR, however, you have the luxury of doing that, where you can physically move up to something and try to examine it really close. And that starts to bring out the problem where your eyes are converging to a certain distance, but your lenses are still focusing at a faraway distance. And things that you would expect to be really crystal clear up front end up going out of focus. And this problem is a tricky one. There's a good deal of research going on, but currently the way developers need to work around this is by knowing this fact and making sure that they don't always rely on things that are right up against your face. For example, if your character needs to read a map, don't bring that map right up into their face. Make sure that it's at a roughly easy to read distance so that it doesn't start to go out of focus. And so that means there's a limited comfortable range. And to make the point about our current headsets, we tend to have our accommodation distance that is roughly 3 meters or far away, meaning that your eyes will naturally feel like they're actually focusing further away than closer. The other problem with VR, it's what's called the vestibular-ocular mismatch. Essentially, in a nutshell, it's what's the bane of all VR programs, and it's simulator sickness. Essentially, what it comes down to is the fact that your inner ear is saying you're stationary because you know you're not moving, but in VR, you're maybe running down a hole if you're playing some badly written VR application, or maybe, hey, you know, you're playing Team Fortress that came out a while ago and you could run at like roughly, I think it was 30 miles per hour, 30 kilometers per hour or something crazy like that. So the problem there is that even though the software and the hardware are working perfectly okay, they're fulfilling all the specs you programmed them to do, it still is making people sick. And you need to be aware of this. It's something that requires careful thought. You can't just say, you know what, I'm not going to worry about that. It is definitely a problem. Similar to that point is yaw, or what you do when you're playing a first-person shooter and you're pulling the stick left and right and rotating the camera. The problem here is that a lot of people would think, oh, you know, I never get sick when I'm playing it on my regular TV, but in VR, that will get you sick real fast because it covers so much of your vision that your body, again, is feeling like it's being swiveled, but your inner ear is saying, no, you're not moving at all. So the trick here is to make sure that you have some kind of consistent static frame of reference. Some ways to work around this is by having a cockpit if your game is one of those kinds, like a flight simulator or racing game of sorts. Or you can have some kind of heads-up display that is keeping you locked into that world. When it comes to the Gear VR, you actually have the luxury to use a chair to swivel around instead of relying on the controller. And this is something that has been tried, and it works perfectly well. The only reason you can't do it on the PC is obviously because you start to strangle yourself. So, one way to work around this is what the Cloudhead Games guys have figured out. They like to call it comfort mode, and I think that's a cool name. The idea is that you don't smoothly rotate when you snap the yaw stick. Instead, it rotates at some known increments. It could be 30 or 15 or whatever you feel like your game would work nicely with. We actually have this in our Oculus World demo sample as well, and if you guys want to try it, you should definitely give it a go and see how it feels. So, after talking about all of these things, the major complaint we started getting after we released the DK2 was this notion of judder. And it started to happen because our VR experience fidelity went up really high. The positional tracking and the low persistence where the screen is now flickering and not always on. It started to make people realize that you need to account for every single frame that is being rendered. The problem is there's multiple reasons why you might see jitter in VR. You know, one of the most common cases is the application is just simply not rendering fast enough for the HMD. But then there's other cases like the fact that you might be just doing incorrect predictions and your predictions are all over the place, so the rotation is all over the place. Or maybe you're just doing bad simulation of physics in your game if it relies on that kind of thing. Or like I was saying previously, you might have a bad USB hub where it's not giving the info at the correct time it should and the quality of service is really bad. Or you have some bad GPU, you know. We tend to shy away from laptop GPUs when we're having people try VR because they have a lot of quirks that go along with them. So we always are trying to shoot for some high quality and known tried and true GPU. And we've recently announced that a certain set of NVIDIA and AMD GPUs that would give you the best experience. And sadly, Intel doesn't have one yet that we could suggest or recommend. And then there's many other issues. But the problem is, a lot of these errors can also be invisible and still make you sick. And that extra frame of latency, maybe you're accidentally slightly rendering things off by 1 pixel. Sometimes the position tracking isn't working and you don't know why. Maybe you forgot to plug in your sync cable, or you just moved out of the camera range and it's not tracking you. Or we've seen some developers accidentally, because we also tend to vet a lot of VR applications as well, we do make sure that some of the higher quality, quote-unquote, AAA titles are going through our quality control to make sure they're doing the right stuff. And we have seen some really, really weird things going on with their applications, and we tend to help them as much as possible to make sure the VR aspect of the application is really rock solid. One of the bigger problems, you know, I've said graphics is one of the easier parts, even though it's really not, and there's a lot of stuff that can go against the classic intuition. For example, normal maps. We've all seen games use normal maps all over the place. They give you really nice lighting and all that stuff without actually putting the detail into the geometry. But when you have a normal map on an object that's really close up to your face, because VR requires stereo rendering, you'll notice that that surface is actually pretty much flat. So you need to somehow either put the detail into the geometry, or you need to use some kind of parallax occlusion mapping, or what's called steep parallax mapping in this case. But you need to make sure that it doesn't look flat, unless that's what you're actually hoping to do. And then there's the problem of billboards. A lot of games tend to use billboards because, hey, you know, billboards are cheap. You can put them out into the distance, or sometimes bring them close up. You'll have particles that are big quads of billboards, and next thing you know, in VR, because again, you can see the parallax in the rendering, you'll notice that they're just flat quads, and they don't actually have a shape to them. And you need to be aware of these kinds of things. So where you thought a billboard would have just worked fine, you need to make sure that it's selected very carefully. So you can still use, for example, billboards for very far away objects where your eyes, your stereo separation wouldn't be able to tell that it's actually a really flat surface. Similar deal with reflections, for example. In this case, if you look at the screenshot, that application is rendering the cube map and environment mapping that onto the teapot. On a regular 2D screen, that will look fine. But if you were to look at that in 3D, you'd be able to tell that the airplane is kind of going over the surface of the teapot, and it doesn't look like it's actually reflecting how you would expect reflections to be inside the surface that they're reflecting. So you need to be aware of those kinds of things as well. Similar deal with when you're dealing with UI, for example. You need to make sure that your UI 3D labels are also placed properly. Sometimes when you look at graphics, people realize, oh, I need some powerful GPU, and that's really the case, because when you look at all the things you need to do, you're rendering the scene most of the times twice per frame. You need higher resolution, higher frame rate, which many games up to this point have always been shipping at 60 frames a second, and now we're asking you to do it at 75 or 90 frames per second. The problem of, because the GPU is usually operating a frame later than the CPU for regular games, you were able to allow the staggered thing, but the problem there was that that would add 1 frame of rendering latency, and that 1 frame of rendering latency ends up being kind of too much. So in our SDK, we actually added what's called Q ahead, and that is already shipped in 6.01, and we're further refining it in 0.7 and above, but that's essentially to fight against those kinds of problems.